Hello. In this video and the next video, I want to explain a little bit more about what our arrow symbol means and how it's different than what if-then actually means, even though we've been symbolizing if-then with the arrow. It's important to understand these differences in order to really understand what the arrow means, and that's important to truth table problems and derivations, how we're going to approach them, and also just to understand what we're doing and what we're not doing when we symbolize if-then sentences with the arrow. So in this video, I'm just going to look at the arrow, and in the second video, I'm going to compare the arrow and if-then. So conditionals are actually, we're going to start with one observation about conditionals in English. Conditionals are weird. So here are two conditionals. If Lin-Manuel Miranda didn't write Hamilton, somebody else did. If Lin-Manuel Miranda hadn't written Hamilton, somebody else would have. So A is true. How do we know that? Well, Hamilton exists. Somebody wrote it. If he didn't, somebody else did. B is false. If he hadn't written it, would someone else have come along and done it instead? No. So A and B, while they're both conditionals, and they're almost exactly the same, are different. A is true and B is false. And we might ask, well, how do we know the difference? What is the difference? We can summarize the difference by saying that A is indicative, it's about the way things actually are, whereas B is subjunctive, and it's about the way things would be if something that's not true were the case. But that doesn't really, that's a way of sort of gesturing at what the difference is, but pointing at what the sort of grammatical difference is in the two sentences. But if we were going to really explain what the meanings of A and B were, we would need to do a lot more than that. And it's hard. Conditionals are complicated. Fortunately for us, the arrow is simpler than natural language conditionals, but that also means it behaves in somewhat unexpected ways. It makes it fundamentally a little weird as well. Okay, so let's review the truth table for the conditional. On the first row, we ask what happens if P and Q are true, and on that row, the conditional is true. On the second row, P is true and Q is false, and when that's the case, if P arrow Q is false. On the third row, P is true and P is false and Q is true. On that row, P arrow Q is true. And finally, on the row on which both P and Q are false, P arrow Q is true. So if we think about this, there are two rows on which Q is true, the first row and the third row. And on both of those, and those are the only rows on which Q is true. And on both of those rows, P arrow Q is true. And that means that if Q is true, then P arrow Q is also true. So that means if the consequent of P arrow Q is true, then the whole conditional P arrow Q is true, which is a little weird. Also, let's look at the rows on which P is false. Those are the last two rows. And on both of those rows, again, P arrow Q is true. So we know that if P is false, then the conditional P arrow Q is true. So what we know is that if the antecedent of our conditional is false, then the conditional is false. And that if the consequent of the conditional is true, then the conditional is true. So in other words, P arrow Q, when is that false? Only on the second row when P is true and Q is false. Otherwise, P arrow Q is true. So all the conditional really says is it the case that P is true, but not Q is true? No. Is it the case that P is true but Q is false? No. That's all it says, right? So we can think of the situation where P is true and Q is false. We can think of that as a counterexample to the conditional. And then all the arrow says is there's no counterexample. That's all it says. And there are lots of ways there can be no counterexample. P and Q can both be true, P can be false and Q can be true, or P can be false and Q can be false. And if any of those are the case, then the arrow is true. So we can repeat what I said before. If P is false or Q is true, then P arrow Q is true. And there they are. Those are weird things about the conditional. And they're reflected in our derivation system. So these two arguments, Q, therefore, if Q, then if P, then Q, that sentence is derivable. And also the sentence, if not P, then if P, then Q is also derivable. And I'm actually going to now show you how those derivations go. So here we have this is one of these theorems, right? It's a sentence that is or a formula that's derivable from no premises. So we'll go ahead and start. We'll say show conclusion. And the conclusion is if Q, then if P, then Q. So we'll say assume CD, because that's what we always want to do if our show line is a conditional, and that gives us Q. What should we do now? Well, we want to complete the derivation, and the natural way to complete the derivation is with CD. And what do we need for CD? The consequent of line 1, so we need if P, then Q. So we'll say show cons, which means we're going to show the consequent of line 1, so if P, then Q. Okay, good. Now what do we need to box and cancel 3? Well, we need Q. We don't actually even need to make an assumption. We can just repeat line 2, gives us Q. Okay, and then we can say for CD. We're done. Hey, that's pretty cool. It's kind of weird, but it's cool. And then we can say 3. Well, 3 is the consequent of line 1, and so we can say 3CD. And there we are. We've derived that the sentence Q arrow, P arrow, Q. Very easy derivation. Let's look, and we're using this rule R that we've just been learning about in this module. Let's look at another derivation. Let's look at the derivation of if negation P, then if P, then Q. So here we have if negation P, then if P, then Q. So we'll say assume CD. Again, we're going to say show cons because we want to get the consequent in order to box and cancel line 1. So this time we'll make an assumption. We'll say assume P with assume CD. But now we have what we need for indirect derivation because lines 2 and 4 are contradictory. So we'll repeat 2, and then we'll say 4, 5 ID because P and negation P are contradictory, and so that's what we need for an indirect derivation that boxes and cancels line 3. And now we can use line 3 to box and cancel line 1, and again we are done. So there we go. Very simple and straightforward derivations. We don't even really use any real inference rules, right? In the previous derivation, all we did was assume CD and repetition and CD. Here, we do assume CD, repetition, and ID, and that's it. No MP, no MT. We're just exploiting the way assumptions work and the way in which boxing and canceling rules work. So you might think those are weird derivations, but they definitely are derivations. They're correct using our rules, right? Each of those steps was just fine, and so we completed the 2 derivations. Still, they are weird derivations. In neither of them did we argue from P to Q. In neither of them did we argue from the antecedent to the consequent. We either said we already have the consequent, we can do CD, or we said, oh, well, if the negation of the antecedent is true, then we can do ID, and we don't have to get to Q. You might think, well, I don't like that derivation system. And in fact, there are other derivation systems in which you can't do those 2 derivations we just did, in which you can't get from Q by itself to if P then Q. You can't get from negation P by itself to if P then Q. Those derivation systems, though, are based on our system, and they're just more complex. So I think for right now, it's kind of nice that we're using the derivation system we're using. What we want to understand right now is that there are these 2 funny facts, that the conditional box and circle is true if box is false, or if Q is true. And what we're going to see in the next video is that if box then circle is not like this. What we've seen in this video is that we looked at the truth table for the conditional in the logical language and saw, oh, it's kind of weird, and we saw that the derivation system reflects that. And the derivation system has to reflect that if the derivation system and the truth tables are going to agree. And we want them to agree. We want, whenever the derivation system says an argument is a good argument, we want the truth table system to say it's valid, and vice versa. And to have that correspondence, we need to be able to do the derivations that I just did. So good. In the next video, I'm going to talk a little bit about what these facts that we've observed about our arrow show that the arrow has a different meaning in the end than if then in English or conditionals in other natural languages.